Okay, so the cat is welcome to stay or to leave, but needs to take a decision, the cat. Anyway, it is my pleasure to welcome Tomas Latimer to talk to us about asymptotic analysis of Riemann Hilbert problems using Q-calculus. For the Riemann Hilbert fans, this has been an amusing afternoon, I think. So Thomas, the floor is yours. Thank you.
Okay, yeah, so we have covered some of the stuff earlier today, especially in Nalini's talk and Alfredo's talk. I think Nalini was talking a little bit about Q-calculus, and then Alfredo was talking about Riemann Hilbert problems and asymptotics, and then hopefully in this talk we'll sort of combine those two ideas by focusing on a model problem. So, okay, so this whole talk is going to be focused on answering what the behavior of these polynomials are as their degree n goes to infinity. Right, so we have a class of orthogonal polynomials that satisfy this orthogonality relationship. W here is a weight that's going to have restrictions on it put on later, but for now just consider W as a general weight. Probably just needs to be positive. And how we're going to do this is, first of all, we're going to reframe these polynomials in terms of a Riemann Hilbert problem, and then we're sort of going to go through the Dice-Sauer method to strip away the behavior and get some interesting asymptotics. But I would say there is a fair bit of difference between Dice-Sauer because I'm going to try to stay away from like exponentials and logarithms and differentiating stuff and try to stay just in the Q-calculus, which is sort of the natural space to be in for a formula like of this kind.
What does the plus and minus mean?
Oh, sorry. So this will be clear in a couple of slides, but the plus and minus means I evaluate, so there's like two sums. There's one evaluated at plus Q, and then one evaluated at minus Q.
So are these orthogonal polynomials? Like a discrete weight? Or is it?
Yeah, yeah.
They are?
Yep.
Okay. And both of these plus and minus both are satisfied. It's not like you split one or the other.
Let me just skip forward like one slide. And then, so this is it written out properly, right? So this is the plus minus was just taking both sums. Did I skip forward? Okay. Okay, so first of all, to get it in terms of a Riemann Hilbert problem, I'm going to introduce this function h here, right? So a couple of things to note about this function h. It's q invariant, so h of qz equals h of z. Hopefully you can see that from here. H is also an odd function. You can probably see that from here. And why am I introducing this function h? Well, the reason is because I want to take this discrete sum, I want to take this sort of like orthogonality condition of a discrete sum into a nice continuous smooth integral in the complex plane. And so the idea is I'm going to use Cauchy's residue theorem and sort of pick up the residue at h as a summing times by q to the k. And then I get a nice sort of, if you can imagine a contour surrounding the right points, I'm using Cauchy's residue theorem. It'd be like having a discrete sum. Cool. All right. A couple of other things to note about the function h. So as I mentioned, it was q invariant. But another important property, which will come up later, so keep it in the back of your mind, is that h is the only function which is meromorphic everywhere except for poles at q to the k. Sorry, let me rephrase that. If a function is meromorphic everywhere except for poles at q to the k, then it has to be h plus a constant, basically. This comes back later. I'm not going to prove it here. Just take it for granted. Okay, so a couple of things in Q-calculus before we start. I think I'll be quick through this because if you went to Nalini's talk, so you won't have most of it. So we have these Pochhammer symbols defined as follows. The Q derivative, I'm not really going to use it here, but why I put it here is because some of the audience might be interested in the case Q goes to 1 is sort of like can be seen as like sort of your discrete variable goes to like a continuous variable in some sense. So you can see if I took this Q derivative and I took the case Q goes to 1, it looks like a normal derivative. So that might be of interest, but it's not really going to come up in this talk. And then we have a Jackson integral. This is just shorthand notation to save me some time. But the key point I want to highlight in the difference between sort of Q-calculus and differential calculus, which will really become important, is the fact that if I have a second-order Q difference equation like I do here, similar to a second-order differential equation, I can sort of write any solution in terms of a combination of like your two homogeneous solutions. But if it was a differential equation, right, my u and v would be constants, right? Because the derivative of u and the derivative v would need to be 0, so they're constants. But for a Q difference equation, you don't need that. They can be relaxed a bit more, right? This is the only condition you need on u and v. So if I ask u and v to be entire analytic everywhere functions, then they'll be constants. But if I let U and V have branch points or poles, then we get this more interesting behavior. Okay, so try to keep that in the back of your mind as well.
So if you think of this as only living on multiples of q times that, so like it's discrete thing, does that then become constant?
Yeah, yeah.
Okay.
So you think of, yeah, exactly what you said. But try to think of these y's as functions of z in the complex plane, right? So y's are defined everywhere, but the iteration's just in q. Yep.
So but does it always have a second period multiplication by e equal to pi I?
Sorry, what do you mean?
Single value function of z, then you can multiply z by e to the 2 pi I. Yes?
Mm-hmm.
Because I'm just thinking about how it is supposed to linear function to come around. Yes?
Not at this context, not yet. But the elliptic functions come when you introduce another parameter.
Okay. All right, cool. Let's keep going. Okay, so I'm going to flip back and forth between these two slides, but I want this picture in your mind. So I'm going to define a Riemann Hilbert problem shortly for y. So think of always y hat as being like near 0 and y tilde as being near infinity. And we have this jump condition here, dotted line. Okay, I'll go on the next slide. We'll come back there. So this is my Riemann Hilbert problem for which my orthogonal polynomials will be part of the solution. All right, so my solution is here, and you can see the orthogonal polynomials popping in right here and here. Okay, so I have analyticity. I have a jump condition across the dotted curve gamma. I have my weight function w. So now I'm going to impose that w is analytic inside the interior of gamma. This isn't super necessary, but just nice for this talk to go along. And then I have my function here, h. And the reason I have the h, again, is you can imagine I take an integral along this contour gamma. And if I put my h in, I'm going to get back Cauchy's residue theorem. And I'm going to get sort of a discrete sum, which comes in here. I want this to be a discrete sum for yn to be a solution. Okay, details aren't important, but what is important is that my solution is in terms of orthogonal polynomials. So if I study this Riemann Hilbert problem, I get asymptotics. Sorry, if I get asymptotics, I get the orthogonal polynomial. And also I have this asymptotic decay condition. So really I can reframe this whole problem into understanding the asymptotics of this Riemann Hilbert problem as n goes to infinity. Right? So that's what we're going to do. Okay, so how am I going to do this? Well, I'm not going to sort of use the usual techniques where I introduce a g function, although this is a g function in some ways, but I think it's quite a little bit different. So in Alfredo's talk, he had this g function, and then the g function essentially had jumps along where you had jumps, and then things canceled, and then you had exponential decay. Right, so this picture is going to be a little bit different, so I introduced this function here, f. Couple of things to know about f. First of all, as z goes to infinity, f goes to 1, right? So if I look at this this matrix I multiplied here, I've essentially stripped away sorry, let me just go back here. I'm stripping away this behavior. So my function w now goes to the identity as z goes to infinity. Okay, another thing to note is that f has zeros at z equals 1, q squared, and so on. And so these zeros are going to interact with the poles of h. Okay, so these are the two important things to note so far. Okay, after making this transformation, I have a new jump condition. All right, nothing going on there. Okay, in my next slide, this is really how I'm going to strip away the asymptotic behavior. So f satisfies this q difference equation here. You can derive it for yourself. It's just the 1 or 2 lines. And then if I keep iterating this q difference equation, again, this is just induction, nothing tricky going on here. I iterate a bunch of times, I get here. Okay, so what do I want to highlight here? I want to highlight this term popping out. So what this guy's going to do, if I go back to the previous slide, it's going to cancel with this z to the minus n term. Right, and so by iterating this f, I'm getting rid of the z to the n, and that's going to give me a model Riemann Hilbert problem. Okay, so let's go to the next slide. So again, this is my jump. I'll maybe go through this a little bit slowly. So I have my jump, right? I want a model Riemann Hilbert problem. So I want the jump to go to the identity exactly the same way. In Alfredo's talk, he wanted the jump to go to the identity. Okay, so every time I iterate by q, I get a power of z squared popping out, so I choose to iterate by q to the n over 2, and I get my z popping out, and essentially things cancel, and I'm just left with this nice guy here, right? Constants aren't a problem. Constants can be gotten rid of with a linear transformation, and then this gn here approaches a nice function g, right? I'll leave that for a couple of seconds so you guys can believe this. It's, I think it's the most important technique, right? Once you get to the model Riemann Hilbert problem, solving that is a little bit of a challenge, but really getting there is the main point. Okay, cool. Okay, but what does this look like in the Riemann Hilbert problem perspective, right? Because I wanted to shrink f by q to the n over 2. So I wanted my jump to essentially go from this big jump at order 1, and then this little red jump is going to be at order q to the n over 2, right? So my w isn't jumping on this dotted circle, but jumping on this red circle now. But this also introduces poles, because if I go back here, this f inverse term, remember f has zeros, so I essentially what I do is I move poles from this column here into this column here. Okay, so I go through these steps, I take this limit, I cancel out my constants factors, and then I get this nice model Riemann Hilbert problem. So what a model Riemann Hilbert problem is essentially, in the limit n goes to infinity, what my Riemann Hilbert problem looks like, right? Because this model Riemann Hilbert problem will be essentially the leading order behavior. Okay, so this is my model Riemann Hilbert problem. I have a function which is now meromorphic, it's not analytic. I have a condition on the poles. I have a nice decay condition, and I have this nice jump here. So the question is how to solve this problem. You can't solve it using classical means, at least that I know of, the issue being of these poles. So how do I solve this problem? Well, I go back to q-calculus, right? Q-calculus is sort of the natural setting of this problem. Oh, sorry. So this function is just g for those that are interested, because you might be. So g has zeros along a q, so this is a logarithmic graph. These are spaced q apart. So this is like q squared. They just look linear because it's logarithmic. And g grows everywhere in the complex plane. This is just plotted along the reals, but it grows everywhere. It's not like an exponential function. And g satisfies this nice, neat difference equation, which will be important in a second. Okay, so how am I going to solve this model Riemann Hilbert problem? I'm going to make an ansatz that this model Riemann Hilbert problem is solved by some functions which satisfy the q difference equation. That's not obvious at the moment, but it will be in the next slide, hopefully. And then I've got to find this q difference equation, so that's a little bit of work. It's not a mechanical approach, right? It's a little bit of imagination, a little bit of guesswork to find this q difference equation, but it's motivated from concrete grounds. Okay, and then I got to make sure my connection coefficients. So these connection coefficients are related to the u and v we saw earlier, right? Okay, so why do I assume that the solution is going to satisfy a q difference equation? Well, let's look at the 1-2 entry of the jump. So if I go back to previous ones, we're just looking at the 1-2 entry of this jump here. Okay, so I have my tilde, which is my function that's in some ways analytic near infinity, and I have this jump here. And then I've suggestively bracketed off terms. Okay, so this looks really similar, right, to the slide I showed you right at the beginning, where I had a third solution is a combination of y1 and y2, and then two functions which are invariant under multiplication by q. So my h is invariant under multiplication by q, and then I have a constant here, which is obviously invariant under multiplication by q. Okay, so my ansatz is that this whole term in the brackets here, and this whole term in the brackets here all satisfy the same q difference equation. So my goal now is to find that q difference equation. But I also need other conditions on w hat and w tilde. So what do I need? Well, I need my analyticity condition inside my curve gamma. I'm going to find these by basically just expressing w as a power series and then showing it converges and then saying it's analytic. So that's not too bad. And then I also need the right decay conditions. And again, how I'm going to do this is I'm going to express w as a power series of 1 over z, and things are going to converge, and it's not going to be too bad. So what's the right q difference equation to pick? I just picked it here for you. I can motivate reasons why if you want to talk about it afterwards, but now just take it for a given that I pulled this out of nowhere. Why is this the right q difference equation to pick? Well, first of all, I can tell that w hat is going to have a convergent power series. I just make the ansatz. I substitute in w as a power series, and I work out that it's fine, it's convergent. Okay, and I have w tilde as a convergent power series with negative powers of t. right? So this is going to look really nice as t becomes large. It's going to fit my asymptotic behavior of the Riemann Hilbert problem. This is going to solve my analyticity behavior of the Riemann Hilbert problem. I'm going to get my jump basically for free by choosing the right q-difference equation. But then one thing that I think would be of interest to the audience here is I get a divergent power series for one of the examples. So, okay, so you might be like, oh, there might be problems here, right? I have a divergent power series. What I want is I want my w hat over g to look like 1 as t goes to infinity, but now you're like, I have a divergent power series, so maybe it won't look like 1 everywhere in the complex plane. Maybe it'll just look like 1 in one sector, and then you'll have exponential growth and Stokes lines. But I think in the case of Q calculus, Stokes lines aren't such a thing, although that is a somewhat controversial statement. I can stand to be corrected. But the idea is once I see this convergent power series, I don't really get too panicked. I'm not worried about it growing or shrinking in different areas of the complex plane. All that I think that is happening is you just get a bunch of poles, right? So, sorry, let me go back here. What this, divergent power series is representing is the fact that 1 over g has the poles spaced q apart, and these poles have a, they converge at 0 and they converge at infinity. So that's all that this divergent power series is detecting. It's not detecting like Stokes lines or growth in one sector and shrinking in the other sector. That's all it's detecting. And again, we have a growth in coefficients, which looks like this one linear called q to the factorial, which is different, I guess, to the factorial growth that you guys will be used to, or at least most of you will be used to in studying differential equations. Okay, so I think that's a nice point, right? We have this divergent series, but using this theory, I just sort of sidestep it, and I don't even worry about it, which I think is quite neat. Okay, so going back to our Riemann Hilbert problem, I'm going to quickly broad strokes of how to solve the Riemann Hilbert problem. So we start off with our ansatz. So I'm going to call Ws as a solution to our q-difference equation. So we construct a q-difference equation. We see that it has solutions. We see that these solutions behave nicely at infinity and near 0. And now we want to show that the connection matrix is exactly the jump of our Riemann Hilbert problem. So we want our connection matrix to look like sort of like a combination of constants and the function h. Right, but how do I know that the connection matrix looks like this? It's not an easy problem. And so this problem, you can sort of cheat because, in fact, you know that W11 will be an even function. I guess you can believe this from the form of this matrix here. So you know that W11 will be an even function and W12 will be an odd function. You know that G is an even function. This comes from the definition of G, right? And you know that h is the only odd function which satisfies h of qz equals h of z with poles. You need to have poles at the zeros of g, right? If c had a pole that wasn't at the zeros of g, then my w here couldn't be analytic near t equals infinity, right? So I need my poles to line up with the zeros of g, and the only odd function that can do that is h. And the only even function that can do that is a constant. Right, so immediately I can conclude that C1 is h and C2 is a constant, and therefore I know that my two connections here are exactly the connections of my Riemann Hilbert jump, and the problem solved in some sense. Well, I'll talk about why it's not exactly solved. Okay, so I want to highlight here what I really exploited, which is somewhat unfairly and somewhat not a general approach, is I really exploited odd evenness to find my connection coefficients for h and a constant. Without odd evenness, it's much more difficult because finding these, there's no, I'd say, mechanical way to find these connection coefficients where you can just apply a formula and you know it's going to work. Okay, so let's summarize the approach we took. We had a model Riemann Hilbert problem for which we had no idea what the solution was. We made the ansatz that the solution satisfied a q-difference equation, and this was sort of motivated by the fact that our jump looked like a connection matrix. Then we have to find that q-difference equation and then solve it and show that all our properties of the Riemann Hilbert problem, in particular analyticity, asymptotic decay, and the jump condition are all satisfied nicely. And then we have to show that the connection coefficients are exactly the connection coefficients that we need for the Riemann Hilbert problem. Okay, and then there's some linear scaling, which is nice and easy to do. So we haven't exactly found the limiting behavior of P, right? We just found the model solution, but in fact we have to show that so the jumps approach each other, but we have to show the actual solutions approach each other. Again, I think Alfredo skipped over this in his talk because it's quite a mechanical approach. In here, it's a little bit more difficult because we have this infinite pole situation. So I'm not quite sure how to get it in a really nice, neat form. It's like you can do it, but it's not such a nice and neat form as it would be in the more classical case. Okay, so this is the main theorem that we got in this talk. So if W is analytic, sorry, I totally skipped this. We also assume that W of 0 is 1. So where did that come in? When I was taking the limit of my model Riemann Hilbert problem, I assumed W was 1 because you'll notice at some point W disappeared. That's not such an issue. So under these two quite general conditions, analyticity can be relaxed. Then we have the polynomials have a uniform behavior, right? So we can study the polynomials in two regions. These two regions naturally arise in our Riemann Hilbert problem from our shrinking of W. So we have one region where this function is really related to f here. This is basically f, where our polynomial looks like z to the n times by f. And then we have another region where our polynomial looks like this function psi, and this function psi here is a solution to our model Riemann Hilbert problem. So, all right, so I'm not going to write it out here, but suffice to say that, I mean, psi isn't a function of n, and psi can be written as a power series, which is entire and converges everywhere. So you almost know everything about it. Okay, and then I have factors like -1 to the n over 2, which some people might look at it and be like, oh, why is there factors of I coming around? But in everything I did here, I assumed implicitly that z was even. And the reason I did this is because when I iterate this function f, I get a z squared out. So if I want the iterations of f to cancel with the power of z to the n, then I need n to be even. Okay, and we get another little bonus information from the Riemann Hilbert problem by looking at, I mean, just other constants in a coefficient matrix. I don't want to go through the details, but the point is you get this function gamma n, and you get this guy here, an. An here is the recurrence coefficients of the polynomials. If that means anything to you, that's good. If it doesn't, don't worry too much about it. But I would just want to mention that they're related to Pain-Levé equations, which, of course, as a student of Nellini's, I study a little bit. And another thing I want to highlight is that this gamma n is independent of the weight function, right? Which is quite an interesting fact. So if my weight function satisfies these two conditions, which is just that it goes to the identity, and you don't even need that it's analytic everywhere, you just need that it's analytic inside our curve gamma, which we can deform, then our norm is independent of the weight function, right? And I think this is quite interesting, and it was an unexpected result. And I also want to highlight here, this order of q to the n is the smallest order, is the smallest error you can get on your estimates. But it can be larger if W approaches the identity much slower than a certain rate. Okay, so here's some numerics. So this is a function which is one of these functions which satisfies analytic weight everywhere, and it has its weight satisfies these two conditions. Our blue line here, our blue dotted line, is our model, is a solution to the model Riemann Hilbert problem. So this would be like our psi solution. And then our red line is the scaled Q-Hamid, so I just scaled them so that they're in the same place. This is essentially this factor here that I'm scaling out. And we can see the agreement is really good, right? So this is n equals 8, and already the agreement is really, really good. And you can imagine, so this straight line here is to be expected for a polynomial of degree 8, right? It's a straight line on a log-log plot. And you can imagine as I increase the degree, what happens is I just keep getting these zeros. I get a 0 here, and then I keep getting more and more zeros. All right, so I just want to highlight the agreement is really, really good, even for small n terms. Okay, so here are a couple of sources for those that are interested. So the theory here was sort of based on dice work, but it wasn't exactly dice work because we don't use this g function and these exponential and what do I want to say, like the logarithmic potential that comes in most cases for those familiar with orthogonal polynomials in Riemann Hilbert problem theory, but rather we use this whole Q stuff. So the idea is similar in the fact that you take it to a Riemann Hilbert problem, you strip away the leading order behavior, and then you see what happens. But the way we went about it is almost completely different because we want to stay using Q calculus and not sort of these logarithmic potentials and exponential functions that we used by Dief and Zhao, and why this was called, is called the steepest descent method, and also its relation to WKB. Whereas I can't really see the relation to WKB in this setting, but maybe someone else can, and they can tell me. Okay, so Birkhoff really describes the this Q connection matrix. And so essentially what this work is combining the work of Deift and Birkhoff. And then the last reference I put in here isn't so much related to this talk, but is for those that are interested. And in this reference by Ramis, Soloy, and Zhang, they talk about a Q-Borel transform and these diverging Q series, right? And I think that's an interesting thing, that the fact that we have, I still find it interesting that we have a divergent series, and almost for the past week we've been having divergent series and talking about what the behavior looks like and trying to get an idea of what they look like in different areas of the complex plane and where the jumps are and what the order of the error we can get. But here we had this divergent series, and almost it was completely irrelevant, right? We saw a divergent series, and then all we say is, okay, there's a bunch of poles which accumulate at 0 and infinity, and that's all that's happening, right? So it's in some ways so much more simpler, even though the series diverges so much faster because it's diverging as q to the n squared, which is much faster than n factorial. Okay, thank you very much.
Is there any talk? Sorry, thank you, Thomas. Are there any questions or remarks? Yeah?
Hi. You didn't impose almost any conditions on that weight, right? So you're working like on a lot of generality.
So these two conditions?
Yeah.
Yeah.
And I'm not saying it's wrong, but it's just almost unbelievable that you will have the same behavior on the recurrence coefficients for any family with any weight. Could it be that along the lines you impose something?
It's analytic everywhere.
Yeah, well, okay.
Okay, but you don't need analytic everywhere, right? So there's other, so I think it's the Q Jacobi. I always get switched up with my names, either Q Jacobi or Q Laguerre. But so W can have nice, if W just has 1 or 2 poles, it's not too bad because you can deform your contour gamma. Really what's important is analyticity in the contour gamma. So you can deform your contour gamma.
Okay, I understand. Let's put it another way. Did you compare your results with some of the other known results on asymptotics and it matches up?
Yep. There's not too many known results for Q stuff.
No, I know, but...
But yeah, I haven't found any contradictions yet. If I did, I wouldn't have presented it.
No, just in the context of q-orthogonal polynomials. Okay.
Is your problem that it doesn't depend on the weight?
Yeah.
That's the same with orthogonal polynomials on, say, -1, 1. They're always, they have the same asymptotics.
Yeah.
Class in itself, right? Here,
On compact support.
here it could be like almost anything, apparently, and I find that very surprising.
Well, but the spectrum is the same for the, so the weight has the same supports. I was just wondering, can you do anything if k is greater than 1?
If k is greater than 1.
Or q.
Q. Yes. We have the theory. So wait, let me just go back to the first slide. Okay, so q is greater than 1 is really changing this orthogonality from being like compact to non-compact, right? Is that what you want to?
Well, then it'd be an unbounded. Well,
Yep.
the Jacobi operator would be unbounded. But
Yeah. We have theory that's related to that. I'm not sure there's any cases where. My short answer is yes, but it looks different. You go through the same approach of getting a model Riemann Hilbert problem and solving a Q difference equation related to it, but the steps are different, right? Like the steps are the same, but what you end up with in each step is different. So you've got to think about it a little bit.
And are there sort of analogs of these, but with only algebraic? So this has like exponential behavior, so it's sort of exponentially approaching 0. Are there analogs of weights like this where it's only algebraically approaching 0?
Not that I know of.
Okay.
And we were looking in particular at the Q-Freud polynomials, the ones that are associated with Q discrete Panlevet equations.
But the theory is beyond Q-Freud polynomials. We looked there and then we found more general results. Yep.
Trivial question, but I just don't So you say that W is analytic everywhere, but the W participates only on the lattice.
Yeah.
So there might be, or you have some uniqueness result about W. So I mean, if I have, can I have two different analytical W, but which coincide? You cannot. Yes, if it is analytical, because Q is less than 1. Yes, you have accumulation
you have the
point.
accumulation
Yes.
point at 0. So.
Okay. Yeah.
But I wouldn't get too hung up on the analyticity. You just need an analytic near, like, you just need an analytic in a neighborhood near 0. You don't need an analytic
Okay.
everywhere.
Yeah.
That's
Yeah.
just,
Yeah.
Yeah, but imagine how you could deform this contour, right? All it needs to do is encapsulate the q-lattice points. That's all it needs to enclose. So W, you could get rid of a lot of messiness of W by deforming your contour the right way.
May I also... You finished? Okay. So again, very kind of starting points on when you make this first transformation of Riemann Hilbert problem. I didn't quite see. So what's the role of F?
Sorry?
What the role of F of Z? So it seems very, very important.
Yeah. So F. Okay. So F can be seen as the G function that Alfredo was talking about earlier, and that stripping away leading order behavior.
No,
in
but
some sense.
okay. If I consider orthogonal polynomials on the circle, so here again, gamma. What is gamma?
This capital gamma.
What is gamma? Yeah.
Gamma is the jump, which is a circle which encloses your q-lattice points.
Yeah. Yeah. So it is a circle. Yes.
Mm-hmm. Yeah.
So if yes. So if I do orthogonal polynomials on the circle, I would have this transformation, okay, just without any F, of course. So, no, okay, okay. I have to digest. It's something. Thank you.
It's also related. Sorry, it's related to, I don't know if you know the work of Bach, and when he looks at Riemann Hilbert problem for orthogonal polynomials on a discrete lattice, a more general discrete lattice, one of the key steps is you introduce this function with zeros at the points in your discrete lattice. And there's also one of the key points of F is that it has zeros at the points on the discrete lattice. But we can talk about it later if you want.
Are there any more questions?
Instead of jump, with G function, instead of intervals, you have zeros. No, okay, no, I have to digest it.
It's an interesting talk. Are there any further questions or remarks? No? So if you okay, I can. I think we should close this session for today. And don't forget, and first thank Thomas again. And please do not forget about